So welcome, my name is Nicolai Josuttis. I will 90 minutes talk about something I did never understand completely. I only have written books about it. So together, but the good thing is the other author was an expert and still is, David van der Voorde. We wrote together C++ templates, the first edition. It was my task to make it somehow readable for guys like me. And after a few years, we were wondering ourselves, shouldn't we have an update? Because this book was written and published even before C++ 03. So we had some discussions going around, and there was some interesting argument. One schedule constraint is that we are a little bit in a state of flux regarding some of the biggest changes. For example, a new language feature called concepts, which, as you probably know, was removed then. So we came together and we didn't have much progress when we started. And what do you do if you have no progress? If two people don't get the job done? You get a third one. Unfortunately, that didn't help us because all three of us were pretty overwhelmed by other tasks C++ caused us. But nevertheless, finally we made it, and it was published last year in October. So I learned a lot. This time I even read the whole book, which was not the case in the first edition. I can say it now. Now I'm older and wiser, and the age of career is way behind. Okay, so now let's talk a little bit about what I learned, about some updates, even some improvements, which I learned recently. So 2 or 3 times I had already the feeling when I learned something in the past half year, I asked David, for example, oh, wait a minute, do we mention that in the book? He said, yes, in this reference section there, over there, there's a little paragraph. And I said, yeah, but I mean, because it's important. So yeah, it's still not complete because it only has 822 pages now, and that's not enough. Just to explain templates. And for example, just looking at type traits, the first book introduced the general idea. We had 40 pages. Now in the next book, we have 120 pages just about type traits, explaining the concepts and having a reference section about the standard type traits, which might sometimes give the impression everything in templates is about type traits, but that's not the case. That's just a basic tool we use to write generic programs. So, and we have now, for example, a type hierarchy, which is not pretty well known in the whole community, so that we have a classification of types and using type traits to classify between classes and unions. Interestingly, structs and lambdas are all the same type category. And a lot of design follows this type hierarchy. Okay, that's for the beginning, to get warm. Now let's talk about a couple of issues, a couple of things that changed over time, a couple of improvements, and maybe some improvement that will come. And the first thing, of course, we have to talk about is auto. Auto was introduced, as you know, in C++ 11. To, well, help us not to get early problems with our hands. Because whenever we have to use an iterator, we have to write 20 to 40 characters. Something like this, type name T iterator, could be replaced now easily by auto. Good, we all know that, we all use it probably. So, but auto had been used in a couple of other places. Note, by the way, that this is even more generic code because the requirement that the type you pass has a type, a subtype. Iterator is gone now. It must not have it anymore. So this is to some extent more portable, more flexible, and more dangerous. Okay. What happened with my focus? So, we have other places where to use auto now. A more interesting discussion is return types. So, we could say in the past that a function returns a type named C iterator. That should be a T iterator, of course. And in C++ 11, we introduced a trailing return type syntax. Again, we could get rid out of the need that type T here has a type iterator by using auto and trailing return type definition, and that means we can use here the DecoType of what is returned by C.begin. So if I call begin for the pass parameter, I can use it. Which immediately raises the question, why do I have the same to write the same expression twice? So in C++ 14, of course, we introduced just to use auto and no longer specify ourselves the return type. This raises a couple of interesting questions regarding style guides. So should we use that or not? Or when should we use that or not? I think even in the last year, discussed in about 5 companies style guides about using auto. And so let's think about it a little bit. Auto I equals 42. Is this good style or bad style? I would clearly say this is bad style. But we can discuss about this. Auto future is initialized by something I pass to std async. Do I care about the type? The reason the first thing is a bad style is because I care about the type of I, usually. I want to know whether it's an int or an unsigned int or long or whatsoever. For future, it might not be that important. It may be, it may be not. Then we have the issues where we use auto instead of an iterator. Usually people think this is a good application of auto. Then we have the range-based for loops where we can use it. Have to make sure to use it by reference, not to make a copy of the elements in the container or in the range. And then we can discuss the different areas of return types. We can even specify when the return type is clear, like here, a function returning clearly an int, then having a template that is also returning type T, or we have something that depends on a call we do on a passed argument in the template. So I would consider 2 of these at least being pretty bad or really bad. I would not recommend that. For everything else, we can discuss it. The usual outcome is in style guides that auto should be used with very much care and very restricted. At least in 2 style guides, we came up just with explicit mentioning, listing these situations where auto is okay. And that was only by initializing objects for lambdas and in a for loop. Is this good advice? I want to give you one example where my whole value system broke down regarding when to use auto or not. We introduced in C++ 17 a class called StringView. You have to replace StringView by as bad as a raw pointer. So this is a string as bad as a raw pointer type, which is worse than a string reference. And the problem is that this type has no longer value semantics. It refers to something, and its validity depends on the lifetime of another object that is not under control. So some character sequences outside this object, you have to make sure that whenever you use StringView, the character sequence is still valid. Some other restrictions apply, like not necessarily having a null terminator at the end, and the data might be the null pointer. Okay, we are talking about templates. There are a couple of problems with StringView in itself. There are a couple of good things, especially performance. But here's my example that make me worry. Let's implement an operator plus for taking two string views. We haven't standardized such thing. We could. The important thing is if you pass in two string views, you create a new temporary object. So probably the output should be a string, a new string with its own value, so a value type. And for example, implementing like this, convert the two string views to a string, their operator plus is defined, and you return that as an std string. I expect people will do that sooner or later in many code bases as a convenient function. Okay, now let's use a code base where this is defined and use another function, another nice function we have. We have written a very simple template. The template is named concat. It takes two arguments of type t and adds them or concatenates them. You can replace a name by sum or something like that. And of course it returns a t because usually for each and every type the sum of two t's should be a t, and if not, it would not compile. Of course it would not compile. Well, we have an implicit type conversion from std string to StringView. So that means the moment I call concat with two string views, this compiles without any warning. But it's a nightmare. Because what you create here is the following situation. You pass in two string views, you create a temporary string, and you return a reference or a pointer to this value, which is, the moment you return it, deleted. So it's as bad as returning a pointer to a local object. Because we have this implicit type conversion from string to string view. We have it because it's cheap. Because it's cheap to use a string as a string view. So we have an implicit type conversion there. So this works. So this compiles, I should say. So this creates a string view referring to a string that's no longer there. And using it as undefined behavior, you are using a value that was freed. Who made something wrong here? So who to blame? We can discuss it at length. John is proposing the first guy did something wrong. What did he do wrong?
You don't need that.
You don't need that, and so therefore you shouldn't do that?
Yeah, we don't need that because we already have string, and string already provides that for const star and the overloads do.
We don't need that? So you think it's not a useful operation to concatenate two string views?
We already have it in string.
Yeah, but if you have it in string, he's saying, but then you need an explicit conversion here.
Why?
No, you have to do something like this here.
I wouldn't pass around a string view. I would have it as a parameter only.
Okay, John is a smart guy. He wouldn't do that because you don't need it. I immediately wrote that for myself because I was starting with some simple examples, In the simple examples, I was just replacing string arguments by string views, and I saw that sometimes I concatenate them. So I was wondering, why don't we have a plus for string view? And I thought, yeah, it's easy to implement. Just return a string and you're done and you're safe. So what's the problem? Well, I at least make this mistake, so it's my fault. Okay. I would say that this is fine code. Here in this code, there is no memory leak. There is no violation of any lifetime issues. It's okay. So why not? And it might not be that easy. This here is the more interesting part. Following my rules about templates, I said, here I should not use auto, here I should or might use auto. Some people have this interesting rule, almost always auto. So use auto whenever you can. This rule can't be true in C++ because it would be too simple. So, what's wrong here? First of all, you wouldn't have a problem if your template would be declared to return that the return type is auto, deduced by the compiler. Because in that case, this would return a string, and then with this auto, x and xy would be a string. And everything would be fine. Okay? The other way to solve that is don't use auto here. Because if I use here string view, immediately an alarm bell should ring. And if I use string here, everything is fine. Why not? Oh yeah, you're right. My first mistake. So this is a key point. Good that you tell me. So this is the first time where I saw, beside convenience, that auto is better than the intuitive type. Yes, you can think about it and say, yeah, maybe it's not that intuitive, but okay. Good. So we have thought a bit about templates, auto now. There is more than auto. There's auto-ref-ref and DecoType Auto, which are the other things for generic programming. And if auto is that easy, auto-ref-ref and DecoType Auto should be also there. So why do we need them? We have perfect forwarding, which you probably all know. You could take a variadic list here of arguments as universal references or forwarding references. We have this strange situation that nobody invented a term at first, and then Scott Myers invented the term that was widely used, and then for whatever reason, the standard committee decided to use another term to confuse, just to confuse the Russians, probably. So, okay. It's C++, yeah. So, in any case, if you want to forward something, that's what usually you learn in trainings about modern C++. Declared as universal or forwarding reference and forward it. Okay, that's easy. Now, what happens if you want to forward something that is not a parameter? You have here a return of a function calling compute. This might be part of a generic function, so you have no idea which type T is. You have no idea what the return type of computed is. It might be a value, it might be a reference, or whatsoever. So you pass it directly to process. That's fine. That's perfect forwarding of a local object. So, but if you want to split this in two sets, then you need auto-ref-ref. That's the application of auto-ref-ref, saying I want to have here a universal reference, and whatever is returned here by this compute, the nature of it, or the value category of it, should be preserved in the call. So you have to call, you have to initialize an autoref, and you forward it by the type of this object and by the value of the, taking the value of this object. So we introduced that. Good. Was it good enough? Did it work for everything? No. We have more. We have the case that we sometimes want to perfectly return something. So if we perfectly return something, what should we use? Because the problem is, if we return auto, the return type is auto, it decays. So we lose move semantics, for example. So now you might think, as a naive programmer, well, I learned just perfect forwarding for something that is not a parameter. I should use autoref, of course. But whoa, no, that's a reference to a local object. So don't do that. That's a fatal error. Fortunately, the compilers can detect that usually. So for that, we introduced DecoType Auto. And that's the way you should do it. So now let's combine these two things. Let's have a local object as a return value and then return it later. Should we internally use autoref and then with the return type be DecoType Auto? No. There are other rules. Oh, I have a different slide here. Why that? Good. Let's first talk about DecoType Auto as how it works. DecoType Auto uses the rule of DecoType to deduce its type and its value category. Well, I should say it's to deduce its type, and this might happen according to the value category. So if you have DecoType Auto and return by name an object, it takes its type, because that's the rule DecoType is implemented. But if you return an expression, then the rules of DecoType for expressions are used. And these rules say we are taking the value category of this object into account, which is not a problem if you have something like I plus I, because I plus I is a temporary object. A temporary object is a PR value, and for PR values, DecoType deduces just the type without being any reference at all. So this return type is int. But I hope you all know that if you return I in parentheses, some of us have this style, putting parentheses around the turn statements, then this becomes an expression. It's an expression for an L value because I has a name. And that means that the deduced type here is a type of I plus one reference, so as an L value reference. So the return type of this is int reference, which obviously is not okay here. Again, returning a reference to a local object. So, okay, the only thing we learned from that is don't put parentheses around return statements. It's funny, because I'm now teaching modern C++, so I'm really wondering when to introduce this rule. Should I say it from the beginning? Should I later say it's when to use DecoType Auto? It creates some interesting problems that we have this issue now, that in a rare corner case, it changes the behavior of the program if around the return expression you put parentheses. Okay, now we come to the other problem. I thought my slides are the other way around. So let's call a function internally in my template, use a return type, and then return it. Again, we have two options. We could say autoref here and DecoType Auto here, which is, by the way, again wrong. So here you have to use DecoType Auto here and here. Otherwise, you again have a problem with your lifetime issues. Is it all? You see a couple of gaps here. Well, which problem do I have in this code? Who can tell me? This DecoType Auto does not work for incomplete types, and void is an incomplete type. So if this is generic code calling a function that returns nothing, this does not compile. So the real way to do this is pretty simple. You use a const exprif, which we have now. We check for the result of invoking this, whether it's void or not. And if it's void, we just call it and return nothing. Otherwise, we use the returned value and return it. Some people argue, hey, Nico, don't complain. Because anyway, you have to do something different. Because here you have a return with a value and here not. Okay, that's a valid argument. So I give it to you. But anyway, I'm a little bit frustrated about these things. These, by the way, were funny. When we wrote the templates book, pretty much at the end, I discussed all these things. So I said, so I now learned everything. So I now know how to perfect forward and how to perfect return. So let me summarize the rules. And that was the beginning of these slides. So, and by the way, this is something that will hopefully fixed. I think this is not fixed yet, but that DecoType Auto will work for incomplete types, and then you need only this line and everything would be fine. So, let's talk about variadic templates. Totally different subject. Let's look. We started in the old template world. We didn't have an ability to have an arbitrary number of template parameters, so we had to overload, sometimes with some tricks, templates for multiple arguments. So in tier 1, the tuple type was overloaded for between 1 and 10 different types, or you had to use default values somewhere. So this is possible, and this has been possible, but it was a little bit, well, interesting. Especially if you wanted to support a print with taking 100 arguments. So we can do better. We can say something like this. So we can say, I have a variadic template now, taking a variadic list of arguments. We call ourselves recursively, and we need an end criterion. So in this case, the end criterion is just the print taking one argument. The funny story with this is that this was formally invalid in C++ 11, but it worked with every compiler. And we fixed this in C++ 17. So this is formally okay since C++ 17, but since C++ 11, you could do that. And the point is that the rule was that if you overload templates and both can match, this is always an ambiguity. There is no priority between these two things. But implicitly, all compilers took the first one more important than the second one if both match. And again, standardizing existing practice was this time really done now. So the effect is that we just expand the first argument and the remaining arguments by calling print again, and effectively we compile. Thus the output lines, you know that. Okay. So now we have C++ 17, and code like this is pretty boring to write. So we have introduced fold expressions. Who's familiar with fold expressions? About half of you, or not even the half. This is a new feature in C++ 17 to be able to avoid the recursive application of operators on all the past function arguments. So here you have a parameter pack, a list of variable, a variadic list of templates. And here I can write, we have different syntax for that, but in this case, I use a fold expression. The syntax is in parentheses, ... and then depending a little bit on the exact details, in this case, you have twice to write the operator you use. This twice has to be the same operator. Here you have an initial call and then you place your parameter pack. And if you then pass this, for example, for 3 arguments of 3 different types, this will expand to first you printing out std out to std out the first argument, then to the return value the second argument, etc. So this is what is done and performed here. So that's it. No longer the need for recursive calling of templates, which, by the way, reduces compile time, because recursive instantiation of template is far more expensive than here just instantiating this template once. And the compiler can now here iterate over the elements internally. Unfortunately, we have a problem, a little problem. We have no space in between. And we have only this syntax in a way that you say you can pass 2 arguments beside the operator, an initial value and the parameter pack. So how to place a space here between the arguments? Well, we have templates, so we can do everything. By the way, I should say, of course, in real-world code, we would pass the arguments by const reference here. So now let's put a space in between here. And the space in between here, we simply do as follows. When we print out the arguments, we no longer just print out the arguments as they are. We first, before we take the arguments, print a space before. And you see what this does here? Space before takes the argument, prints out the space, and returns the argument again. So this does the same as here, but the moment I call this, I have immediately printed out a space. If you write code like that, you are lucky if it works accidentally, because it's only working because we had established another rule in C++ 17, which is a guaranteed evaluation order. Because before C++ 17, it could have happened that space before would have called even before we start with the first output, or before we use them. So if we use call before, space before for 10 arguments, we might print 10 spaces and then use the output of this. But we fix that because it's a usual source of confusion to think about that this might be called and evaluated before or otherwise then reading from left to right. So this is now fine. It's guaranteed code. It will work, and it will do what we expect, print the elements. Now, we can do better, or we can do different. There's nothing in C++ where you have only one way to do it. And there's nothing seriously in C++ that can be done without lambdas. So let's use lambdas here. Look at this. Instead of having another helper template here we define our lambda. The lambda is printing out the space and the arg. So this is a slightly different approach. The lambda is taking the argument and printing the argument and the space before. So therefore, it's cout space and then argument. And here we use again a fold expression. And this fold expression is using application of the comma operator. So we are here calling one after the other an application of, for each template argument here, an application of this lambda for all the arguments, comma separated with a semicolon at the end. Easy, huh? And of course, we do it only not for the first argument. So for the first argument, we have a special handling. We have a special parameter for that, which is just printed so that we only have spaces in between. And C++ wouldn't be C++ if you could write that even more condensed that way. This is for fold expression internally using the lambda that for each element adds a space before the passed argument. Easy to read. Okay, so are we done with this? No, there's something more. What we have also now in C++17 is two things. We have an improved way to deal with strings as template parameters, and we have an ability to use auto and template parameters. So look at this. If your template wants to use a string literal, you could, even in the past, declare the template to take a const character reference. You can't instantiate a template for a class type, but this is possible. The only problem was in old C++98, this object you pass has to be a const character array or pointer, which has external linkage. So outside any function, with extern, you had to initialize this, and then you could instantiate this template for this literal. This got improved with C++11. In C++11, you no longer need external linkage, but you still need linkage. So you still have to be outside any function, but this extern is no longer necessary. In C++, 17, we made the next step, which is you need no linkage at all, but you still need an object. So you can now have a static visible object, but without any linkage, declare locally and pass it here. And guess what will happen in C++20? Probably you can directly here pass the string literal. We are working on that. Good. Another feature we have is you can now use auto in a template non-type parameter. You can, for example, parameterize your template by the message it uses. Think about this as a class that has a stable prefix writing into a log file or something like this. So you can instantiate this template for any type which is possible for auto and is supported by templates, by non-type template parameters. So you can pass a character, you can pass an int, you can't pass a double because still templates are not allowed to be instantiated for doubles, for floating point values, and of course you can now pass a static string literal this way. So why do I tell you that? We can now do the following trick. In our print statement, where we want to take an arbitrary number of arguments and put a separator between all the arguments, we can now parameterize this with auto, a separator. So not necessarily a character, we can use auto here. The default is to take a character being the empty character. And that means we can call print for 3 arguments, and it will split a space between these arguments. But this template also allows us to put another separator here, for example, a dash as a character, or now with the new way to pair strings, here a string, for example, comma space as a string. This will work, compile and work. And of course, in one statement here, having the lambda as part of the fold expression. So this is already the application of 4 different C++17 features in 5 lines. We will have more about that. Just for the funny guys here at the ACCU, the feature is not that templates can use auto, they can use placeholder types. So you can, of course, also use DecoType Auto here. And I fear there will be useful examples in the next ACCU conference for that. So what this does, if you pass an int, everything is fine. But you follow here the rules of DecoType Auto. So you can do the following now. You can say, I have an external int, and I instantiate my template for an int including parentheses. The important thing is that this x inside parentheses, because this makes x, or this uses the rules of DecoType for expressions, not for entities. And that means, because this expression, again, this is an L value, so for L values, this yields the type of the object as an L value reference. So you instantiate this template for int reference. Which means if you then print out, print out any message here, it is 42, but if afterwards you take the argument times 10, it will output 420. You like that, huh? Okay. Having said and already introduced lambdas, let's talk about lambdas, because lambdas is a big success story. And the funny thing is, lambdas is just a more convenient way to program with templates. So, because it's an abbreviation of a function object where you have internally, of a function object, and especially if the lambda is a generic lambda, the member function, being the function call operator, is a function template. So let's look at about how to use and benefit from this and what this means. We have a new type in C++ 17 called std variant. It's a type adopted from Boost, and it is a union type, the better union type. It has some advantages. For example, any object knows which alternative, which of these two different types it currently holds. So this object is either an int or a string. As I initialize it with 42, it will currently hold an int with the value 42. The moment I assign hello as a string or string literal, it will has the value of a string literal. So what you can do here, you can use function objects to generically use this variant. For example here, function object saying if I get an int, I print the int with the prefix int. If I get a string, I just print the string. So you can now say visit with this function object, my variant, and whatever the variant currently holds will be used here to print. This is, Louis today had already a talk about that at the beginning, saying we all know that. I'm not sure whether we all know that, but this is to some extent a locally programmed virtual function table. Here's code generated that looks at runtime which type it is, at compile time with the checks that for each and every type there is a function call operator supported here. Good. So why am I talking about templates here? Well, besides we are using templates. Well, first of all, if I do the same things with all the types, I can use a member template here. So I can say my printer takes an arbitrary type if I use this printer as a function, so my function object used as a function, and for any type, I just print the element. And that's exactly what happens if you use a generic lambda. So if you, instead of this, write code that directly as the first argument passes a generic lambda, printing the element, you have this semantics. With some benefits, the biggest benefit is template, this code can only be written outside any function. This code can be written and be used wherever you need it. And that's one of the reasons this is a success story, and people hate that. Except the people here at ACCU, they like that. But that's a different story. You are special, you know that. Okay, so I can explain this even to beginners. We teach Lambda as one of the first tools we ever teach when teaching modern C++ now, because it's more or less self-explanatory. What happens if I want to do the following? I want to have different behavior in my function object. So I want to have either, for any type t, print out the element, but for ints, I want to have a prefix int before. There are a couple of options, and I think I missed one. Yes, I missed one. I don't have a slide on that. Because the first thing we can do is we can, inside the generic lambda, we can check the type of the x. And then use if const expr, so the compile time if, and depending on the type, choose the right thing. Unfortunately, I forgot the slide about that, because it's not that easy. If you just check is same the DecoType of x against int, that's not enough, because that's in const int reference. So you have to decay this type, and that will work. And that works. I tried it out. I just forgot the slide. But do we have another chance here? Instead of using template code and a function object to write it manually, can we here use lambdas? Yes, we can. Of course we can. Because we can program the following. Look at this. This visitor is using two lambdas. In fact, it's overloading the functionality of two lambdas. Look at this. One lambda for any type, print out the value, and especially for the type int, print out the value with int before. Detlef is looking very, thinking about, you know how to implement this, don't you?
Probably I could use a tuple.
A tuple? No, the trick is not a tuple. The trick is a lot more simpler and uses two C++ 17 features. So how can we arrange that this works? This is a trick. We have a function object that derives from a couple of function objects. Okay? So, you have multiple base classes. For each type of one lambda here is one base class. So, as you derive from both base classes, from a base class defining this lambda and a base class defining the function object for this lambda, you have two implementations of the function call operator in the function in the base class. And by using the operator of all base classes, this application of variadic templates, you are deriving all function call operators of each and every base class, so of each function object. The only problem we have, normally in structures and functions, we have to specify explicitly the types of the base type. But that's not necessary because we have now deduction guides. We have a new feature call that we can say you can skip to specify the arguments of a template if they can be deduced either according to a constructor, we have no constructor which helps here, or according to an explicitly written deduction guide. And we say that here. We say for a variadic template, if I call try to create an object of this type, taking an arbitrary number of function objects, please expand this to an object being as a template parameterized for all these function object types. In other words, what this overload is doing, it's initializing an object of a class template, a class struct template, I should say, or template struct. We pass as initialization two functions objects. According to this deduction guide, this will deduce the types of these lambdas as template parameters, and these template parameter types are the base types of this object, of this data type. And then we derive their function objects. Straightforward coding, isn't it? Yeah, that's all. It works. So we combine the C++ 17 feature variant with a couple of new features. One is in C++ 17, aggregates that have base classes are still aggregates. So otherwise this would not work. We would have to write a more complicated constructor here, but we don't do. We use here aggregate initialization, which passes these arguments to the base classes in the order of their classes. This feature is used here, and we have this deduction guides used here. Cool. We are discussing currently to introduce this even in the standard library, and then this would be called an overloader. So we can visit an overloaded function object containing different functions objects. Okay? Good. There's no fun anymore. Good. Const expr. Let's talk about const expr. Const expr is in a way interesting because this is an application of the trial no longer to use templates, where we are fed up with template syntax. I should say that one problem we have in templates is the following. Templates weren't meant to last. When we introduced templates, we didn't know that we could do something like template meta programming or something like that. I remember in 1997, Erwin Unruh came up with a little program. And the program at compile time was printing prime numbers as error messages. And that was a proof that the template metaprogramming mechanism is a primitive recursive language. So we can compute at compile time. The syntax is really screwed up for that. It is. I mean, who likes to write code like this? This was at the beginning of C++ using templates. We had here written a code that is computing whether a specific and given number is a prime number. And there were a couple of restrictions. For example, to get any value at compile time, we couldn't use something like const expr or so. We had to use enum. Enum was OK. So we initialized an enum value to get this value at compile time. Then we had a couple of restrictions, like there could be only one statement, etc. But by interesting combinations of different helper templates, we could find out whether a given prime number is a prime number at compile time using template syntax. So is prime 9, for example, was here expanded to do is prime 9 and 4. This is here the expansion. And then we check whether divided 9 by 4, so 4 was half of 9, therefore we start with this. And then we check down, we go down and check for each and every number whether we find the divisor of 9 that yields 0. So for modulo, for the modulo operator. So, and we do that by expanding this template again and again, and we have some special rules for the special numbers 0, 1, 2, and 3, where 0 and 1 are no prime numbers, and 2 and 3 are prime numbers. When we started that in 1919 something, we got in a lot of problems. So for example, after, I don't know, 10 or 20 instantiations of the template, the compiler crashed. Or the other reaction was that the resulting symbols were so long that the compiler crashed. Okay, so we fix this to some extent in C++11. So that we no longer have to use enums here. We can now use static const x per values. These static const x per values can be initialized directly, so that makes it a little more readable, but still we have to use all these different overloads of function templates to program what we want to. By introducing const expr in C++11, we got a new way to do that, and that was that we just write an ordinary function, and with const expr we say this can be used at compile time. Just to clarify, const expr is introduced as a keyword just to save compile time. So what we say with const expr to the compiler is, hey compiler, it's worth to try this out at compile time if you have to. Because we could have also said each and every function is implicitly compile time until we find out that it's not. And if a compiler would act then, they would try out everything they need at compile time, and then until the point where you can't compute this at compile time, and that would take too much time. So we don't have to specify this is for const expr at compile time. It's just saying, compiler, it's worth to check this, to use this at compile time. So we do the same here because we had some restrictions in C++11 that there was only one statement allowed, which had to be a return statement and only using literal types or other const expr functions. And then the big thing was changed in C++14. Now we can use here more or less each and everything that's supported by at compile time. So control structures, especially multiple statements, multiple return statements, etc. What is not supported is something like new, delete, virtual, static. GoTo is not supported. GoTo is not supported. If somebody would tell me that in my team, he would get fired. Okay. So, yeah, no, I know. But now we get the syntax that can everybody read, and we use here no angel brackets. We just can use this function wherever we need it, and we can use it. And yeah, that's the way we made the use of templates here no longer necessary if we compute something. So if we have compute something numerically or whatsoever, this works fine. The moment we have to deal with types and conditional compilation, then we still need templates. And by the way, we will extend this feature. This feature will be extended in C++20, for example, to support something like simple allocations, dynamic stuff. and so that we will have the ability in const expert code, for example, to use a vector with a default allocator. And we need that, and because we want to have collections at compile time. One application of this is that at compile time we want to use collections of something for reflection. Reflection needs a list of something, a list of all the members, a list of all the functions, a list of all the arguments in a function, and that's a collection type, and we want to be able to use vector there only using the default allocator. Sorry, John. No pool allocator there. Okay. Good. So this is also interesting. When something is very useful, we try to avoid the nasty template syntax. It happened with lambdas. It now, the second time, happened with const expert. And we will get more. So to some extent, there's a pattern saying we like what patterns do, although it was not invented that way. And the more we like it and the more we use it, the more we hate the syntax. So the more likely is that we replace the syntax by something useful and readable. And that will probably continue. So I think we can take bets about the question when in C++ in general you can use auto in any function, implicitly converting this function to a function template. Maybe C++ 26. Maybe not. Good. Another example of this is enable if, and here we also have learned something when we switch to templates. Sometimes the rules in the language are really strange. One of the strangest rules is that in general the copy constructor is called unless something else fits better. And normally template code doesn't fit better except when it fits better. And that's a source of confusion again. It would be a lot more easier if we would have said the copy constructor always fits best. But there are probably good reasons why this is not the case, because usually we have a couple of strange rules in the language, but unfortunately, in most of the times we have good reasons for these strange rules. At least according to some value system, which might not be always my value system. Good. Here's the example, the classical example. We have here a function, a class, a customer class, and for whatever reason, we have written a generic constructor taking the arguments as a universal reference and forwarding them into the member. This is, by the way, not the way you should do that anymore, but sometimes you need it, especially with implicit type conversions involved here. And to the surprise, you can initialize now, for example, something that converts to a string here, and as an argument, if it's a const, or if it's a customer, or if it's a const customer, but a customer, a non-const customer, can't be initialized, this has to be a 1, by a non-const C1, while a new customer can be initialized by a constant customer. So why that? Because this is a better match than a copy constructor in this case, so in the case where we pass a non-const object, because for the copy constructor you have an implicit conversion from non-const to const, and that's worse than taking the template. So therefore, this does not compile. We have a couple of examples in the language that fall in this problem, in the standard library that falls in this problem. So what is the solution? Well, you simply have to specify that this function, this generic constructor is not available if it shouldn't be available. So in fact, if you pass something that better uses a copy constructor. So we say here, we are initializing a string, but we only enable this whole constructor if this data type here can be used to construct a string, otherwise not. And as there is no implicit conversion from a customer to a string, it will then be disabled if we now pass here a customer. That's the famous enable if. The syntax of that was modified over the years. This is one way to write it. If we use C++17, we can now do two things. We can, instead of enable if without underscore t and type name and : type, just write enable if t. That was already possible with C++14. And is constructible v can now be used instead of is constructible : value. So that's just little things. Unfortunately, the right solution didn't make it into the standard yet, because again, this is pretty nasty syntax. We use all over this standard library. So we made this pretty nasty template syntax to a language feature. And the language feature is part of concepts and will be just a keyword requires. And we just write what we require, and we say that this function to be used requires that we can construct a user type to construct a string. Otherwise, this is not available. This is part of the concepts library, by the way, or the concept. This is, however, not a concept. It's a little bit bad that those who proposed concept thought if we then can use requirements, they always have to be concepts. That was their argument to not accept this for C++17, because this is not a concept. This is just a technical way to specify a requirement, a constraint on the ability or visibility of this function. This is just a technical workaround. This is not a semantically concept I'm introducing here. Fortunately, we could reject that I have to introduce a concept and then use this concept here. That will not be the case. So, that's it. That's all I learned, or that's all I came up with from what I learned in C++ about the past years about generic programming. So I'm not using all the 90 minutes. I think templates are a success story. We hate the syntax. So the moment we love a lot of applications of this, then we make this language features, and then suddenly things become successful even in the mass. That's visible with Lambdas, that's visible with cons.exp, and that will be, well, requires is still a technical feature to some extent, at least motivated in my example, because it fixes a flaw we have in the rules of classes. But anyway, because application programmers from time to time might have to do that. So we have, here now a better syntax coming. Not a perfect syntax, but at least better. And that will probably be the case in future. So I'm curious that what will be next. Just some advertisement. You saw a couple of examples here. I know a little bit about C++ 17 now because I have written now, or am about to write, 2 books that cover C++ 17. We have covered C++ 17 in the C++ templates book, although we didn't see all the consequences we see now, 1.5 years later. And I'm currently writing a book about C++ 17 in total, which lists both all the language features and all the library features. I gave yesterday a tutorial about that. I think those who attended will agree that C++ 17 is a little bit more than just a few fixes. And so there is a couple of things to say. And the interesting thing is here, at least, this book is already available, although it's not done yet. I use a new model here, an agile approach, where we can say that this book is already available. Half of the book is probably done. And you can get it at LeanPub. Here you find the direct website of this. And then you get updates for free. It now is therefore cheaper price. It seems I'm the last lonely author of C++, at least one attending the standards meetings. This takes a lot of time, so to be honest here, I welcome if you buy something like these books. And we are still looking forward to C++ 20, and if you want to have a special discount, there is a discount. I'm happy if you don't use this special discount and pay more. No. So this is advertising by bringing you to the website without benefit from this advertisement. So let's see whether it works. So that's it. Thank you for the attention. Again, apologize. I'm not a C++ template expert, but that's the things I learned and saw as an application program, and that's my view of the story. And next time, I promise I tell you more about the library where I'm a little bit more familiar with. Thank you very much and enjoy the conference.